Alright students, welcome to Mr. Wong's electronic channel. I bet you must be thinking what we are doing today, right? And today we are going to do semiconductor diodes. Alright, awesome man, let's go, right? Okay, now first things I want to share with you before we start. Okay, what are we going to do today, alright? Now, so this is what we're going to cover. Basically, if I were to sum up everything in this chapter, it will look like that. Okay, so we are going to do, alright, the structure of a diode, yes. Okay, we are also going to cover diode operating regions, yes. Okay, now, and these are the three things that I want you to know, right? The ideal diode, no forward voltage, right? We don't analyze the forward voltage. Okay, normally this is found in section A, right? Section A will be mostly on ideal diode and things like that. Okay, just 1 or 2 marks only. Simple, quick analysis. Don't have to do problem solving. Okay, just straightforward. Now then, the simplified diode that contains forward voltage. Okay, forward voltage. Right, that will be in section B. Alright, and practical diode has forward voltage as well. And this will be in section A of the exam, very likely to come out. Right, it has come out once or twice in the last 3 years already, so you better make sure you pay attention to this part. Alright, so in section A of the exam, they will test your understanding on the working regions of a diode. Okay, working regions of a diode. Now, following that, operating in the what about applications of diodes? Okay, so operating in the breakdown region. Okay, we have the Zener diodes. Okay, over here the Zeners. Alright, we also have the those that operate in a forward bias. Okay, the LEDs. Okay, definitely we need to cover LED, right? Talk about diode, light emitting diode is also a diode. Okay, so 7 segment is just 8 or 9 LEDs arranged in a certain way. Alright, in a certain rectangular format. Okay, then you get your 7 segment display. Okay, and then yes, this part here. Alright, converting AC to DC. Okay, in chapter 5 we learn about AC, right? Now AC power is not very usable by many electronic devices, so we must convert AC to DC. Yes, AC to DC, right? Okay, so using the half wave rectifier. And then, of course, the best is to use the full wave rectifier. The full wave rectifier is going to be the best stuff on earth. All right. Okay. So you have to get this right. Okay. The full wave rectifier will surely be tested. Okay. All right. Now, of course, the next thing we're going to talk about is in chapter 8. Chapter 8 itself also has this infrared and photodiode combination. That is operating in reverse bias but not in the breakdown region. Okay, we'll cover that in chapter 8 video. Okay, Ken? Right, we are good to move on. Now, so the structure of a diode. What do we do in the structure of a diode? Okay, what do we need to know? Alright, what do we do with this word? This word is super important, structure of a diode. Okay, I have already highlighted it. Okay, over here, structure of a diode, right? It's not for fun that I highlighted this. Okay, because many people didn't know what's the meaning of the word structure. So most of them will think that this is the structure of the diode, but no, this is not the structure of the diode. Okay, all right, this is not the structure of the diode. So please take note of it. All right, the structure of the diode is this one. This is the structure of the diode. Okay, so when you are asked to draw the structure of the diode, you must take note of the anode, the cathode, and the PN junction. Okay, this part here you must label it correctly. So this is the structure of a diode. Okay, when you're asked to draw, which very likely you'll be asked to draw. Okay, in the national exams, this is a section A question. Make sure you get it right. Okay, Ken? Alright, next. Okay, so how does a diode work? Okay, how does a diode work? Right, now. Oops, wrong. Let's try that again. Okay, so how a PN junction diode works. Alright, if you look at the slide, okay, we see the diode basically works in forward and reverse bias, right? I think this one by now you should know already. Okay, so VD is the voltage drop. This one is the voltage drop across the diode. Okay, we now know that this VD is actually VF lah, right? Okay, the forward voltage. Okay, then you have different types of diodes have different amounts of forward voltage. Okay, and ID is known as the diode across the current. Okay, normally for standard diodes is about 1 amp, around plus minus 1 amp. Okay, they can only take up to 1 amp. Any more than that is too hot, they will burn. Okay, so basically that's about it. Okay, for this slide. Now, so like what I say, the forward bias, if it's connected in forward bias, the light bulb lights up. Okay, standard one. These things you should know by now. Okay, forward bias in the correct direction. So how do we know whether a diode is connected in the correct direction? Okay, diode usually go from positive to negative, right? So if you draw, let me teach you a trade secret. How do we draw, how do we remember the structure of draw the symbol of a diode? The symbol, not the structure. This is the symbol of the diode. Okay, symbol of diode is drawn like that, right? Plus, okay, going towards minus, right? There, your diode is here. There, this is your diode symbol. Okay, let me draw it properly again. It should be like that. Okay, got a rectangle here. Okay, like that, right? So you see the plus here, right? You see the plus here? This is the plus, right? Correct. Now the plus going towards, okay, the arrow pointing towards the minus, right? And then going forward. So this is how you remember the structure of a diode. And then LED is just extra 2 arrow coming out to show that got light coming out. That's all only. Easy, right? Easy, right? Okay, make sure you get it right. Okay, so forward bias, this will work. Okay, so going from plus to minus, no problem, it will light up. But when it goes from minus to plus, okay, this is called reverse bias, right? Not say reverse bias, it always don't work. Later on, we look at some exceptions, okay? Sometimes it works in the reverse bias mode. Some kind of diode only. Okay, but most standard diodes work in the forward bias. Okay, that's why in the first slide, right, I show you already, right? Which one in the first slide? You remember the first slide or not? This one I show you, right? Which one operates in the reverse bias? This one operates reverse bias, right? Correct or not? This one operates in the forward bias, right? This one operates in the reverse bias, right? So different types of diodes have different workings. Okay, so take note, but most of the time this is the standard one, the standard diode. Okay, so take note of that. Okay, so when I'm talking about this one is the standard diode, not the Zener, not the photodiode. This is the standard diode. Okay, so this standard diode doesn't work in a reverse bias, right? Okay, you can see the bulb does not light up. Okay, and how does the diode behave? Okay, the diode behaves in this way. Ideal diode will behave like that. Okay, so in an ideal diode situation, by right, this thing will work. Okay, so 100% transmission of all current goes through. Okay, and assume no voltage drop, right? Of no forward voltage. Okay, ideal diode, no forward voltage one. Okay, right? So over here, also same thing. Alright, if the current flows this way, this is reverse bias, right? So 0. No current will pass through, blocks everything. Okay, so it's like as good as a open circuit. Actually, basically, this slide you don't need to remember anything. I just remember forward it works, reverse don't work. Okay, simple, don't think too much. It's just like that only. Okay, now this is the graph. Alright, this is the graph. Okay, a lot of students don't take note of what is the graph label. In this case, this graph is a graph of current across the diode versus voltage across the diode. Remember, okay, basically you want to see that when it goes across a certain volt, did it have any current going through or not? This graph shows you this. So basically, what this graph is showing you is when there's no voltage drop, okay, this part here of the graph, right? When there's no voltage drop, it is an open circuit, right? Because no voltage, no current, so 0, 0, everything's 0 here. Can you see? Okay, you increase the negative current by -1, -2, -3, you still be 0, 1. Okay, you have voltage flowing in the opposite direction, right? -1 volt, -2 volt, -3 volt. It also gives you 0 current because wrong direction, right? Not? But once if it's correct direction, okay, it plus 1 volt, plus 2 volt, plus 3 volt, right? Don't care what direction, it still goes up. Okay, you plus 1 volt here, it also let go all the way through. Basically, after 0 volt, it gives you full current only. Whatever current you have, it will give it to you. So if let's say the maximum current in your circuit, right, is 1 amp, so then this will stop at 1 amp, it will be this high only, understand? So this graph basically just shows you this. This is the ideal diode. Okay, ideal diode. Ideal diode. Okay, most of the time, for quick analysis, we assume ideal diode condition. Okay, Ken? For quick analysis, but let me tell you, once the question didn't say there's an ideal diode, right, it gives you the forward voltage, right? Don't assume anymore that it's an ideal diode. It's not really. Okay, Ken? Later on, let me show you. Okay, let me show you. Okay. Okay, so like this is what I said just now. Okay, for quick rough estimate only. Okay, normally ideal diode won't come out for exam one. Normally normally sometimes will come out. Okay, sometimes, but most of the time, if it come out in section A, only in section A, it's like 1 or 2 mark question only for quick analysis. Okay, once they give you the forward voltage, you must not assume ideal diode only. Understand? This one very important. Very important. Once you get a forward voltage, given the forward voltage in the question, it is not ideal diode anymore. Understand? Okay? So this one you must take note of this. Alright? If you need, replay the video again. Okay? Replay the video again. Okay, next. Practical diode. Alright, since ideal diodes don't exist, okay, we normally use real diodes, okay? So we call it a practical diode. Alright, so silicon diodes, germanium diodes, all these are all practical diodes. Okay, let me show you the real diode. How does it operate in real life condition? Okay, so this is the working regions of the diodes. Okay, now I'm going to show it to you now. This one very important. Very important. Will come up for exam. O-level exam test. Two times it has been tested. 2 times. So if I tell you it's important, you better make sure that you study this part. Okay? Okay, now. Okay, this is the real practical diode. Okay, practical diode basically has 4 regions, right? 4 working region. This is the reverse bias. Reverse is here, reverse. Okay? This one forward. Okay, same thing. This one is a graph of ID versus voltage across the diode. Okay, so what this graph is basically telling you is this. Okay, VK normally is the knee voltage is the forward voltage. VK equals to VF. Okay, equals to VF normally. Okay, the forward voltage. Now, so if this is VK equals to VF, let me write properly V. This is VF. Okay, VF. Okay, VK is equals to VF. So this part here normally is 0.7 volt, right? If you know for most diode it's 0.7 volt. You can try. Sometimes it's a little bit lesser, sometimes a bit more. Okay, but most of the time it's about 0.7 to 0.9. Okay, so after 0.7 volt, the diode lets go. Oops. Okay, the diode actually lets all the current through. Can you see? The current actually goes in an exponential direction, which is as good as free flow already lah. Okay, so if there's 1 ampere here, okay, going across the diode, so it will basically be here. This is the amount that you will see. Can? Okay, so don't worry about this. Basically, this graph is just telling you that after 0.7 volt in the forward bias, if free flow current, that means it's as good as turn on. Okay, in the forward bias region. Anything less than here, this part here, right? This part here, okay, is also in a forward bias, but not working fully yet. So you can see the current is considered almost close to 0. As good as not mentionable. Even here got small current, right? You can see here got one small current here. Can you see? I'm circling this point here. Okay. This point here got some got this point here. Yeah, I erased already. Okay, let's do that again. Okay, over here, okay, got some current here lah. Okay, but normally in most situation we don't bother on that because it's so small. Maybe like 0. Maybe 0.05 amperes, that kind of 50 milliamps or less, maybe a little bit less. Okay, can maybe 0.03 yet. Okay, so not worth mentioning. All right, so small current cannot do anything also. Okay, can. So basically, this graph is just telling you after 0.7 volt, then the practical diode will work fully in the forward bias mode. Okay, then for the reverse bias, right? This diode is working in the reverse bias, right? So there are two regions, C and D. C and D is in reverse bias. Okay, can you see? The C I just circled, right? Can you see C and D is working in the reverse bias? So when you're working in reverse bias, normally it will only become fully conductive after the breakdown voltage. See, after breakdown voltage, right, it behaves just like after the breakdown voltage, right, you see, oh, wow, suddenly the current free flow here. Same here, it looks like the same point here, right? Can you see? A here and D here, also same pattern one. Can you see not? Okay, so what I want to say is this. This part here is fully conductive at here. But what does it mean? Does it mean that we can also operate this voltage at the breakdown region, this diode as a breakdown region? No, this is actually normally 50 volt. Okay, 50 volt. Actually, you want to spoil, this is called breakdown region will spoil the diode one. Okay, so basically, don't push the diode beyond what it can tahan. Understand? So 50 volt is the maximum. Okay, 50 volt. This one is 0.7 volt. So 50 volt, basically you push the diode to a maximum point already. At 50 volt, it will let go all the current. So after that, normally the diode is spoiled already. Whether it's forward wire, it will behave just like an ordinary wire. Everything inside burn already. Okay, it will behave just like an ordinary wire already. So it will, whether forward or reverse, it will just let current through already, 100%. Okay, that is normally what happens when you reach the breakdown region and you still refuse to stop the voltage. It means you still push it beyond 50 volts, 60 volts, 70 volts like that. Then of course it will spoil. Okay, so just take note of that. Okay, the breakdown region. But normally nobody do that one. Nobody want to spoil your diode, right? Correct. Push it to 50 volt. Okay, that's quite not normal. But you still must know what happens to a diode when it's pushed beyond its breakdown region. Okay, the breakdown voltage. Right? Okay, Ken. So for more details, you can read this stuff here, which is wow, very long, but basically it's just what I just mentioned. Can, and this part here also. Can? Okay, so you can go into detail and read this on your own. Right? Okay, next. Let's move on. Okay, so practical diode has this is the difference between ideal diode and practical diode. Okay, so practical diode, there's a VK or VF. Okay, VF also, sometimes we call it VF also, forward voltage. Okay, so you need to have a VF or higher. Must be more than VF, then it will turn on. Okay, there is a small reverse leakage current. This one assumes 0 and 0. Okay, Ken? Alright, and then of course, there's no limit for the ideal diode situation because normally application rate of 50 volt, right? At the most I give you is 12 volt only. Most electronic device work on 12 volt. Okay, most, I'm just saying most in your syllabus work on 12 volt only. So you will never reach breakdown voltage one. This one equals to like 50 volt, right? For most type of diodes, you probably won't ever reach 50 volt one. Okay, Ken? So, but then you still need to learn that if you push it to 50 volt, it will spoil the diode. Okay, Ken? You still need to learn this part. Okay? So remember, revise this. This one, let me erase everything again. Okay? This one must revise. Must. Okay? Must okay? Must revise this part here. See? Look at this. It says here, this chart is super important. Will be tested in the national exam. Okay? Super important. Remember to do it. Okay, so data sheet for practical diode. Okay, so this is for your coursework. So for coursework, you have to read data sheet, right? Okay, so won't be tested in exam one. But even if tested in exam, you must know what to look out for. Okay, Ken? Okay, basically if it's tested in exam, this is a giveaway question. But unlikely, okay, I tell you. In the 3 years, this thing never come out. Maybe 4th year, maybe this year will be lucky, but no, I doubt so. Okay, so the breakdown voltage is here. It's called peak repetitive over here. Peak repetitive reverse voltage. This is called the breakdown voltage. Okay, Ken? Alright, then the maximum forward current. maximum forward current is here 1.0. So even though they say average forward rectified current, right? Okay, basically it's as good as saying maximum forward current. Okay, because we normally when we rectify already, right, it is 1 amp already. Okay, so normally you just let pass 1 amp only. Okay, 1 amp. Alright, maximum forward current. Okay, next, forward voltage is here. This part here, can you see? Typical forward voltage is 0.93 for this particular diode that you find in your room. In the electronic lab, okay, you have all this a whole lot of this 1N4001. I got other secret these diodes as well. Okay, you can play with them. Right, you can go and find it inside the 1N4001 box. Go and find it. Okay, 0.93 is the standard. So just now you see the forward voltage was 0.7, right? Okay, 0.7 is the average. Okay, there are some diodes work at 0.5 volt also got. So average 0.7. This one is 0.93, can, but maximum is 1.1. Sometimes the manufacturer have some defect lah, then it can go up to 1.1 or so. Okay, can, some plus minus a bit lah. Okay, can, but maximum is 1.1, the forward voltage. Okay, can, right? Okay, then you see here, it also says here that forward current is 1.0 amp. So Mr. Wong never bluff you. Most diode is at about what maximum 1 amp already. It didn't work already. Okay, can? Okay, so how does a diode behave? Basically, every time when you connect a diode in a circuit, don't forget the current limiting resistor. Okay, this term is important. Okay, where else do you connect a current limiting resistor? Where else? Yes, definitely your capacitors, right? Remember the RC circuit, the R resistor capacitor RC circuit. Okay, you also have a current limiting resistor, right? Now again, this also has a current limiting resistor. Why? Because this guy here, the diode, has no resistance. Yeah, it has no resistance. So it depends completely. What is the then? If that's the case, if there's no resistance, then actually the current, when it's not connected to a resistor, the current is infinite. You know, that's crazy, right? That's going to burn the diode. So definitely you need to have a current limiting resistor to protect the diode. Okay, super important. We will definitely test you this idea, this safety thing in the exam. Okay, for sure, very important. You better remember. You better remember. Okay, remember this. Remember this. Okay, then the simplified diode model over here. Okay, you have this particular diagram. Basically, this diagram is just telling you that there's an ideal diode with a forward voltage. Basically, that's it only. Okay, simplified diode model. Alright, so when it will only operate after the forward voltage is achieved. Okay, this is basically this diagram just trying to tell you this. Alright, but if it's very confusing, heck, don't bother about this. Okay, can? Okay, basically, remember, right? This is the simplified diode model. ID versus VD. Okay, after the forward voltage, right, equals to mostly on average 0.7 volt, right? After the forward voltage has been achieved, it will let go all the current. See, the current goes up exponentially, right? Correct not? This looks like this, right? Can you see? Can you see the original graph? This is the practical diode. This is the practical diode model, right? This is the simplified. So if I put it side by side, right, you will see actually this part I don't need to care lah. This part here, the D, I don't need to care one. You will never hit 50 volt. 50 volt, how to hit? Negative 50 volt. Okay, this is minus 50 volt. Wow, crazy. You will never hit one. Okay, can? So most people play only around this region here. Okay, so this one is as good as here lor. This one goes to here. Can you see? Then this B, assume this part here is so small. This part here, right, is so small that it's negligible. So actually can consider as like that. Okay, as 0 volt. Okay, no, sorry, not 0 volt, 0 current. So got 0.7, 0.6 also can consider as 0 current. Okay, can. Then once you hit the VF, then it goes up. Can you see? Once you hit the VF, it goes up, right? In the practical diode, this one also same thing. It goes up, lor. In the simplified diode model. So basically, if I were to erase everything and show you again, basically it's just like that. Can actually this simplified diode model is even more simple to understand already. Can? Okay, and most of the exam question will use this simplified or practical diode model. Okay, basically, both are almost the same thing. You can consider it almost the same already. Okay, can? These two. Alright. Now, so this book example is very important for you to know. Okay, like I say, right, the diode has no current. So sorry, the diode has no resistance. Okay, so there will be a current across the diode, but it will be decided by the current limiting resistor. I say again, the current limiting resistor is like a mid shield. You know what's mid shield, right? That means it actually helps to decide the current and takes up all the and takes up the rest of the voltage inside the circuit. So you look here, okay, this D, right? We know that D, okay, in this question, right? Okay, D is, let's say, oh, how come there's no marker already? Let me get a marker. Oh, here, okay. So if this D is 0.7 volt, right? We know. Always remember, diode just needs 0.7 volt. Okay, for assume the forward voltage is 0.7 volt. So you can see, right? So if 5 volt here, 0.7 volt here, then this guy has to take 4.3 volt, right? Correct or not? Make sense? Everything must add up back to 5, correct or not? KVL, I remember KVL. Okay, go one loop, right? Must go back to 0, right? Correct or not? So 5 volt minus 0.7 minus 4.3, right? This is 4.3, okay? So this one will be 5. So this remainder here, the 4.3 volt, will be absorbed by this particular resistor. Okay, so now do you know why it's called a mid shield? Because if you increase the voltage here, this thing will take whatever that's increased. Understand or not? Okay, so remember that. Okay, so this guy will take whatever voltage that's left over. Okay, and then this whatever leftover voltage over here will decide the current in the circuit. Can you see? Using the I equals to VR. So current only appears when there is resistor, right? So can you see the importance of the current limiting resistor already? Without it, the diode's current is super high. It's very dangerous to connect a diode like that. You'll spoil the diode immediately. So normally, we definitely must connect a resistor across the diode. Clear? Okay, the resistor has a special name. It's called a current limiting resistor. Okay, can? So let's move on. Okay, so yeah, so you can still calculate the power dissipated in the diode. Okay, using this, only this formula can be used because you have the current, you have the voltage, right? You can calculate the power. You cannot use P equals to I squared R or P equals to V squared over R, right? You can't use these two equations. Why? Because you don't have R. Correct or not? You don't have R. This R is not found in the diode. So these two equations cannot be used. Understand already not? To calculate the power of the diode cannot run. Okay, so make sure that you use this equation in P equals to IV for diode, for the power dissipated in the diode. You use P equals to IV. Understand already not? Okay, normally the V is 0.7 okay, you guys know already, right? The V is definitely 0.7 in order to work. Okay, can or 0 in the real life situation maybe about 0.93 okay. Just now you saw, right, the earlier data sheet is 0.93 but for most exam question they will take forward voltage as 0.7 volt. Can? 0.7 volt. This magic number must keep remembering. 0.7 volt forward voltage. Okay, can? Okay, so AC to DC current. Okay, this one is very important. This has to do with converting alternating current to direct current. Okay, this part, please take note. Okay, let's move on. Okay, so diodes can be used to convert AC to DC through a process called rectification. Okay, there are two types of rectification, half wave and full wave rectification. So these two are very important. Okay, half wave and full wave rectification. Okay, now let's start with half wave first, because in order to understand why the full wave is needed, then you must know what is the half wave first. Okay, so let's have a look. Let's have a look. Okay, this one was what I just mentioned. I'll just skip this slide. Okay, so this is the half wave rectifier. So basically, if this is the battery, right, connected to the battery, right, and then it will go in this loop. Okay, so can you see there's a basically this R is known as the current limiting resistor, right? Current limiting resistor. Okay, this is the current limiting resistor. Okay, so when it goes across, if the input voltage is AC, you will have this impact. Okay, can now this is called a half wave rectifier setup. Oops. Okay, let me just erase this first. Erase all. Okay, this is a half wave rectifier. Okay, can now. So now we are using AC. Okay, the uh, AC source. Okay, so when in the positive half, in the positive half, you see positive half, right? So this thing is positive. Okay, of course minus 0.7. In the real one, I got minus 0.7, but we use it as ideal diode. First, see ideal diode. So there's no minus 0.7. Okay, there's no minus 0.7. Okay, so I just erase this first. Okay, so take note. Okay, so it goes here, current goes in here, goes in, output is like that. Okay, 5 volt. 5 volt output, as you can see from the graph here. Can? Now we move on, but in the negative half of the cycle. Okay, the negative half of the cycle, now the current flow this way, right? Correct or not? Now remember the diode was originally in this direction, right? Remember? This is a diode, right? Now, if you go in this direction, this is called reverse bias, right? So when it's in reverse bias, it don't work. Okay, you absorb everything, right? Absorb everything. Remember the graph? Remember the graph? What graph is this? Remember? In negative, it will absorb everything. Can you see here? Negative, it absorbs everything. Correct or not? It becomes zero. It gives you 0 volt, 0 current. Can you see? No, actually it's not 0 volt. There's a voltage across, but whatever voltage you add, anything here, because it's negative voltage, right? It's in opposite direction. The current is 0. See? Current 0. Right now, the current level, this is the current, but it's at 0 point here. Can you see now? This point is 0, 0. 0 current, 0 amps. Okay? So let's get back to here. So now do you understand why this is 0 already? 0, right? So in the end, if I put the two graphs together, this one positive, then this one 0, right? Then you'll get something like that. Can you see now? So whenever there's a negative half here, this part here will go to 0. Can you see? So this is called half wave rectifier. Then why you want to study this? This thing looks like not so completely, because this negative part is not being taken care of. Okay, what it means to us is this. Okay, this one. Okay, sorry. Later on, let me explain this in more detail. Okay, let's move on first. Okay, so normally, just now I talked about the simplified. Right now we are talking about a simplified diode model. Simplified diode model, there is a voltage drop, right? The VF equals to 0.7 volt. Remember, VF equals to 0.7 volt. So it will drop by 0.7 minus 0.7 volt, right? 5 minus 0.7 gives you 4.3 volt. That's how you get it. Can? So actually you drop a bit, right? So original graph will drop a bit. So basically that's what this thing is all about. So it must achieve 0.7 volt first, then you start to go up. So that there's some time before it starts to move up to 0.7, right? Okay, and anything before less than 0.7 is 0. So this part here is being captured here. Can you see? This part here also. Okay, so these two ends are prematurely ended here because haven't reached the forward voltage yet, so we will not register any current one. Okay, any voltage. Okay, can? So sorry. So 4.3 volt, 4.3 volt here, and time in seconds here. So take note of this. This graph is important. You must know, must know. Okay. Let's move on. Okay, so in actual fact, this is what the final thing will look like. Okay, a lot of students cannot get this right. Okay, you must remember this graph. This graph is super important. Super important. Okay, I want to emphasize this. This graph is super important. You will be asked to draw it, and then when you draw it, you must take note of a few features. Okay, you must understand this is very important. The labeling, you must take note of this. V in and V out. Okay, and the time is, and the other one is time in seconds. Okay, and then you look at this. You must draw You must draw 1 cycle and 2 cycle. Okay, then consider as complete. Okay, if you only draw 1 cycle, then how do I know that this is a periodic waveform or not? Correct or not? Is it going to happen again, that waveform? So you must draw 2 cycle, then is to prove that this is a periodic waveform. So that's one thing, okay? And then you must not forget to drop the 4.3, yeah? And then there will be this part here that you must take note, this part here. Some extension here, this part here, all must take note. Okay, so basically, and if I require you to align this, take note of the alignment. It will be like that. The dotted line will be like that. Can? So just take note of this. Okay, this slide is super important. Okay, now problems with the half-wave rectifier. Okay, guys. So basically, the half-wave rectifier is not as good as it is because the negative cycle is not being used. It's being absorbed by the diode. Okay, in the reverse bias mode, right? That means a power loss of more than 50%. Wow, if I transmit a 5 volt, okay, I may only get 5 volt in the first second, and in the second second I get 0 volt. Well, that means what? The light will be blinking. Is it something like that, or what? Okay, I don't want a power supply that dip and goes up, then dip and goes up, and dip again and goes up every few milliseconds. Okay, it will make the light flicker and damage the integrity of the light bulb or whatever electronic device I have. Okay, I want to feed it constant supply. That's good, right? So in order for that to happen, I cannot use a half-wave rectifier. Can? Okay, so actually why people learn half-wave rectifier is to help them to know that half-wave rectifier is not a complete picture of a good rectifying circuit. Okay, that's why we need the full-wave rectifier. Okay, can? Understand already? Okay, let's move on. Okay, so the full-wave rectifier is here. Okay, so basically you'll notice that all the diodes are pointing to the right. Okay, so you remember this one, all pointing to the right. All pointing to the right. Okay, so easy to remember. Mr. Wong give you some tips already. Okay, can? So it's all pointing to the right one. Okay, can? Now, so what does it mean by bridge configuration? Don't you find that this looks like a bridge, like going across, okay, then go back again, like a bridge, okay, can? Okay, so the input is connected to A and C. So input is A and C, top one, okay, then output is B and D. Okay, so you need to remember where the output is connected to. Okay, the diamond, this special diamond, right, where the output is connected to and where the input is connected to. Okay, always remember, top and bottom go to input. Okay, left and right go to output. Understand? Easy that way. Then all the diode point to the right. They can draw already this circuit. Must remember how to draw this circuit. Must remember. Okay, this one will be given marks one. Will be tested one in section A or in section B. This is super important. You better know. Okay, can? Okay, next. Okay, so over here, basically it's just telling you how it works. Okay, so in the positive half, the current flow like this, go like that, go over here like this, then up like that, go that, and then back here. Okay, can? So this is the positive half. In the positive half, the current will go like that. Okay, the voltage will go like that also. Okay, can? Current and voltage flows like this. Okay. So if I were to do this what call that analysis based on not ideal diode situation, this practical diode situation, or simplified diode, right? At the end, I'll get only 3.4 volt because each time we go across one diode, this one lost 4.3 minus 0.7 volt, right? This one come to here again minus another 0.7 volt, so it crossed two diode. So the output later on will be lesser. Actually, it will be lesser like that. And this new output here will be 3.4 volt. Okay, minus 2 times of 0.7. Understand already? Okay, so I really analyze the practical diode thing here. You make sure you get this right. Okay, you must know this part is very important. This labeling. Can? Okay, so this is for practical diode or simplified diode model. Okay. Let's move on. Same thing, negative half is also being taken care of, right? Correct or not? Can you see? If at the negative half, this thing will flow this way, goes up here, goes through here, go up like that, like this, like this. Same thing here, end up also 3.4 volt. Okay, can? Then cross one diode here become 4.3 volt. Okay, here, at the start here will be 5 volt. Okay, same thing, actually same concept as just now, just reverse side only. Okay, so basically it's still rectified, right? And it gives you a 3.4 volt for a practical diode situation. Okay, can? So that's awesome, right? So it captures both negative and positive half of the cycle. You got it. Okay, can? So this is what you get. Okay, if it's an ideal diode situation, let me show you the practical diode situation. Oh, sorry, I count wrongly. It's 3.6 volt. Sorry. See, 5 volt minus 0.7 volt minus 0.7 volt. Oh yeah, my maths failed. Sorry, 3.6 volt. Okay, 3.6 volt here, 3.6 volt. So just take note of this, 3.6 volt. Okay, super important, will be tested in national exams. This graph will be tested in national exams, and make sure you tally up like that, very nicely like this. Okay, so make sure if I've given you this, and then I give you this graph below this particular one, make sure you align it. Make sure you align it. Okay, I want to see the alignment and I want to see all the labeling being done correctly. Can? Can? So 1 mark for label, 1 mark for label, for labels, 1 mark for the key point. Okay, and 1 mark for the shape. Okay, so total this thing will be 3 mark question. You can see, super important will be tested in national exam one. Okay, can please make sure you get it right. Okay, can? Okay, so this one I don't need to. Okay, you want to pause the video now? You want to own self test yourself? Okay, testing over. Pause already. Okay, so now this is what you should draw. Okay, can? Remember all the diodes is pointing to the right one. Can you see? Okay, and then point D and B is connected to the output. Point A and C is connected to the input. Can? Take note of that. Okay, last part. This part are Zener diodes. Make sure you get this right. Okay, Zener diodes. Okay, Zener diodes are the final step in AC to DC conversion. Okay, now, so I'm going to just run through this with you. Okay, the IV characteristics, blah blah blah. I explain the use of Zener diodes to regulate voltage. Now, Zener diodes are used in the breakdown region. Remember, we talked about that, right? Breakdown region in this D, right? Zener. Let me Zener here. Zener is used here, okay? Zener. Okay, Zener is used in the breakdown region. Okay, makes use of this. Alright, but this Zener very special. When it works in the breakdown region, it doesn't spoil. Remember the normal diode, right? Works in the breakdown region will spoil, right? It become a piece of wire. Correct or not? After a prolonged period in the breakdown region. This Zener diode especially works in the breakdown region one. So after you turn it off already, even though it has been used for a long period of time in the breakdown region, it will still behave like a Zener diode. It will not lose its diode powers. Okay, Ken? Okay, so Zeners are very unique. Ken? Okay, so let me bring it to you. Okay, Zeners. Okay, so this is the symbol of a Zener. Symbol, understand? There's a difference between symbol and structure. Many students don't know. Structure is what? The PN thing, right? Remember the PN drawing in front of the first slide. Okay, this one is symbol. Okay, this one, the only difference is that additional part here. Okay, sometimes online you will see them draw additional. They will have a Z symbol like that. Okay, but no, for this course, we make it simple for all of you. Okay, we just do a small little extra part here like that. Can? Okay, so this is called a Zener diode. Then you must know it works in the reverse bias. Okay, Ken? Now, so this is IZ. Okay, IZ, you see, is in the reverse bias one. Remember? So here IZ equals to minus ID. But normally we use IZ. We talk about IZ in the we ignore the minus sign because we expect that it should be working in the reverse bias region. Can? Okay, now. Okay, so just now I talked about the Zener, right? Working in the reverse bias and in the breakdown region. Can you see? Breakdown region. Okay, breakdown region, the Zener diode enters the breakdown region, and then the voltage across the Zener will be held constant at Vz. So that's why Zener diodes regulate voltage is this. Okay, so basically, okay, let's talk about a very simple zener. There's a 5.1 volt zener. Okay, so if let's say if let's say here is 7 volt and here is 0 volt, right? This guy 7 volt will be forced down to 5.1 volt if you are using a 5.1 volt zener. Understand? You understand or don't understand? Okay, basically if there's a 7 volt entry here, by right lah, there should be a 7 volt, right? And this is a 0 volt going back to the battery, right? So this part here, if this part is 7 volt, it will be forced down to 5.1 volt. The rest of the 1.9 volt, okay, is absorbed by the zener. Okay, can? So it will. So this is what it looks like. And VZ is normally there are two values. Okay, normally in our workshop got two zener diodes, two types of zener diode. One is the 5.1 volt one, and the other one is the 12 volt one. Okay, why 5.1 volt? Why so special 5.1 volt? Because most of your electronic devices work on 5 volt, right? Remember? So if you want to regulate voltage, you got a 12 volt AC supply. Okay, you want to convert it, you use a bridge rectifier, just now the full wave rectifier, and then you put a zener there. Okay, you will force it down to 5.1 volt, and which is enough. 5 volt is good for your 5 volt devices. 0.1 won't have much impact one. Okay, can? So all your 5 volt devices, your IC, whatever, all 5 volt, 5 volt, 5 volt one, all can use, all can be using this zener to regulate the voltage for these 5 volt devices to work. Okay, can? So zeners are awesome. And the VZ, right, is very small one. Normally people's normally for most diode, the VBR, right, the breakdown region is 50 volt, right? For zener is about 5 volt or 12 volt. A lot lesser, okay? So take note of that. Zeners have this special quality. Okay, they operate in the breakdown region, and the breakdown zener diode, right? The voltage, right? The breakdown voltage of the zener diode is almost like 5 volt or 12 volt one. Can? Okay, these two are the options available. Okay, there, here, see? I say already, right? Yeah, just say. So take note of this. The 1N4733 is the one that's available in our workshop in big supply. So you can use the zener to regulate your power supply. Okay, can? Okay, like what I mentioned, so if this is 9 volt, okay, then this one drop 2 volt, right? Correct or not? Then here is 7 volt. This zener will force this to 5.1 volt. Was what I mentioned just now. Okay, so this is how it works. Then this thing will not be 2 volt anymore. So it will be 3.9 volt. Understand? Okay, so this is how it works. So no matter what, it must add up to 9 volt. So this guy, if this is working, it will be at 5.1 volt, and then this guy has to absorb 3.9 volt. Can? Right. Okay, so in practice, a load is usually present across the zener like that. Okay, so this load is like can be connected to whatever device, your things that you want it to run on 5 volt one. Because now this line is 5 volt already, right? Anything you want to run on 5 volt, no problem, it can work already. Okay, no problem, confirm can work because this is 5 volt going in and 5 volt going in. Everything you want, you connect in parallel. 5 volt going in, 5 volt going in. So you got many line, 5 volt one, all can work one. Okay, all can work. Just that draw more current. If you add more device, you will draw more current only. Okay, that's all. Okay, all the 5 volt devices can work already. Can? Okay, so to analyze the zener, this one you don't need to know already. Okay, thank God, don't you know this thing already? Can, but basically you need to know how the voltage regulation works with the zener. Okay, now a zener can be used to convert this DC voltage produced by a rectifier into a steady DC voltage. Okay, let me show you how it works. Let me show you how it works. Okay, so you have this, right? Ideal diode, ideal diode looks like that. Okay, so ideal diode situation, you get this graph, fully rectified, correct? But you cannot have 5 volt, 0 volt, 5 volt, 0 volt, 5 volt like that, correct or not? Then how to use it as a power supply? Then every time the light on and off, on and off, on and off, on and off. It will spoil my circuit there. Okay, so you cannot use this yet. Okay, so let's upgrade it. Okay, then I put a voltage smoothing capacitor. Now can you see, right, with the voltage smoothing capacitor, the impact is this new rectified waveform. Can you see? So now instead of 5 volt to 0 volt, right, maybe it goes from 5 volt to 4 volt. Like that. 5 volt to 4 volt. Okay? So 5 volt to 4 volt works better, right? It only fluctuate 1 volt only. So at least minimally, if my power is okay. Sorry. Let me just put it again. So okay, so 5 volt to 4 volt, right? So if I have a 4 volt device I want to run, right, it will at the most have a little bit over voltage by 1 volt. You get what I mean? So my 4 volt device will still work, no problem, because the baseline is 4 volt. Okay, then if I have a 5 volt, right? If I have a 5 volt device, then my thing will on and off slightly over a few milliseconds. Not so good okay, for the device. Okay, so you still need to have one more thing. Okay, so that's where you add the zener. Then it gives you a constant voltage already. Okay, this one okay, this one it works like that. So basically your zener diode, if this is 5 volt zener, right, then your minimum here, the baseline here must be 5 volt. Okay, so this one going in must anything higher 9 volt whatever, or maybe 6 volt this is 6 volt so anything higher than this line, this blue line here, can you see this blue line? This blue line, right? This baseline here must be 5 volt minimum. Then the zener will always continue to work. Understand now? If this thing is less than 5 volt, if this thing is less than 5 volt, this one is less than 5 volt, right, down to 4 volt then the zener the 5 volt zener will not work already, because at some point in time it's less than 4 volt So when it's at 4 volt, right, the zener don't work. The zener only work when the power supply is more than 5 volts. So you must make sure that when it touch here, all the ending here, this one all must be 5 volt. This point here must be at least minimum 5 volt minimum. Okay, this point here must be at the 5 volt level. Then the zener will work at 5 volts. Then anything on top of here, anything above 5 volt, you will absorb and make it into 5 volt. Understand already? So this zener is very powerful one. It is very powerful for voltage regulation, for converting AC to DC supply. So don't forget to connect the capacitor first, then it will work better. If you don't connect capacitor, then the zener will turn on and off, you still have the same problem. So now do you understand how this thing works already? Okay? Now if not, you can revise and revisit my video again if you want to hear me explain this again. Okay, this part here needs a little bit of thinking, okay, to get it right. Okay, now we talk about the easier parts already. Okay, the LEDs. Yes, the LEDs works in forward bias. Okay, why use LED? Because LED are an energy efficient source of lighting compared to the standard light bulb, right? The standard light bulb, this guy only uses about 10% of what the standard light bulb use. Okay, even for very good energy saving light bulbs like the halogen bulbs, right? Okay, they also at least 20% cheaper in terms of energy source. Okay, so 10 to 20%, I would say 10 to 20%. Okay, so they are very efficient. Use very little energy, 10 to 20% lesser than most different kind of light bulbs you can find outside there. Okay, and LEDs, not only that, they also last 10 years or more. 10 years, that's a long time, right? So most of the time, you'll say, hey teacher, my LED spoiled already. At home I got LED light, is spoiled after 2 years. Why? Okay, it's not the LED that spoiled. The LED didn't spoil. It is the transformer that converts the AC to DC. That part spoiled already. Okay, that is the transformer that is spoiled. Okay, that one can only last 2 years, unfortunately. So if you change your transformer, your LEDs will work again. Okay, they are guaranteed to work for at least 10 years. It comes in different colors. Okay, so this one you must take note. Okay, and LED lighting are more expensive. Of course, good quality product must pay more. Okay, not all LEDs can be dim. Some LED cannot be dim one. Okay, special type of LED can be dim. Okay, dimmable one. This is a new technology. But based on our old technology, right? The old textbook one, this textbook one, all the LEDs all cannot dim one. Okay, Alright. Now, most of the time, what is this thing I will test you? I'll test you why use LED over incandescent bulbs. Definitely, I will definitely tell you this. What are the advantages and disadvantages of using LED over incandescent bulbs? You must know, You must know. Electronics students don't know this, it's a joke. Better make sure you know. Okay, Okay, so here, LED symbol with question. Sure, the direction like that, or like this, can or not? Or like that, can or not? Can whichever direction. Actually, make sure the arrow is pointing outward, can already. Okay, make sure arrow pointing outward. Most of the time, whatever direction it is flat, is okay one, because it depends on which side you are looking at. You can reverse this, you can draw it like that, correct or not? Then it becomes like this, correct? If you draw it like that, then it becomes like this, like that. Whatever direction you want is also okay one, as long as the arrow is pointing outwards. Understand or not? The arrow must point outwards, then it's correct. Okay, can? Okay, so next. Okay, this part here, just take note, the physical features, this one you must know. I will give you a drawing like that. Okay, like that. Then here will be cut away one. Let me draw properly. Yeah. Wait, let me draw properly. Eraser, erase this part here. Okay, I draw like this. So this is the normal standard light bulb, right? This one is the flat end. Okay, then the leg. Okay, then this part here is the positive leg, right? Connected to here. Yeah. Okay, and then this part here is a positive leg. This is the positive leg connected to this part. Negative leg shorter, connected to negative leg is bigger one like that. Can basically you must know this is the flat edge. The shorter lip is here, correct? Can you see? Like that lah. Okay, then this is called the anode. How to remember which one anode or cathode is positive? A is at plus. Okay, anode plus. Okay, can? Cathode is Cancer or minus. A come first then C, right? A come first then C. A come first then C. So A come first then C, right? So C is Cancer, so it's minus. So is negative, minus cathode. Okay, can? Remember this. A lot of things also same name one. Anything that's positive is anode. Anything that negative is cathode. A lot of devices use this terminology. So just take note of this. Can? So learn this. Okay, now when an LED is 4 bias, it will have a voltage drop of 2.2 volt approximately. Yeah, most LED is 2.2 volt lah. Okay, can? Don't believe, you can go and try the red color one in a lab. It's about 2.2 volt. Okay, 2.2 volt Okay, to avoid damaging the LED, a current limiting resistor is used. Same thing. LED is also diode. It must have a current limiting resistor. Can? This guy is important. Okay, the current rating of a standard 5mm LED is 20 milliamps. Alright, 20 milliamps very small, no? Okay, LED cannot take very high current so don't put a super small resistor. What normally is better to put about 1K to 10K resistor. Okay, as a protection, this current limiting resistor. 1K to 10K. 1K to 10K current limiting resistor. Understand or not? Anything less than 1K, you run a risk of it being damaged. Better don't. Okay, for 5 volts standard supply, put a 1K to 10K can very safe one. Okay, can? Next. Okay, for the circuit shown in 7.41 blah blah blah. Okay, so you can see the fall voltage is 2 volt. Okay, so if it's a 9 volt supply, you have 20 milliamps as your current rating, then the value of R is this. Okay, 350 ohms. Okay, can? For this particular, no, don't have. Okay, whatever lah. This one you can go textbook and see figure 7.41. Refer to your textbook. Okay. Okay, here. Okay, so this is just another example. Okay, 5 volt. So the fall voltage is 2 volt, right? So the voltage across the resistor is this. Must be 3 volt already. Cause this guy 2 volt, this guy must be 3 volt. It's like that one. Whatever left over, this guy must take. The resistor must take. Okay, so then this guy also decide the current in the circuit. So here you go. At 3 volt over 220, you get 40 milliamp. So 40 milliamp, this guy is 20 milliamps. So the LED will work, will not spoil. Okay, can? Understand already? Current rating, this current rating is 20 milliamps, right? This guy is only 14 only. So now you realize how important the resistor is. Actually, 220 is a little bit too low. It must be at least 1K. 1K, then you guarantee that this milliamps won't exceed 21. Not easy to exceed. Can you see 220 is on the risk of exceed. 40 milliamp is actually just 6 milliamps away from exceeding the current rating. Okay, so just take note of that. Right, let's move on. Okay, now you see a single digit 7 segment LED display that can be used for this purpose, blah blah blah. Okay, so this 7 segment display, right, is always a giveaway in exam. If you get it in section B, most of the time is section B one, section B. If you get in section B, you can thank God already. Wow, this one give away. Why? Because basically very easy to do one. Let me show you. Okay, so your 7 segment can do these numbers 0 to 9. Okay, I think the new one in your textbook, right, will have this addition one. Okay, so take note. So the table here will change already. This table here, for the 9 and the 6. Okay, so just take note that it will change a little bit. Okay, refer to your textbook. Your textbook one is the more accurate one. Okay, can? Okay, to use a 7 segment display, we need to understand its pin configuration. So there are two types, common anode and common cathode. So we'll discuss these two types very quickly here. Very easy one. Okay, this one you should be able to get it. Okay, here, this is common anode. So common plus. So you see, all the positive is all connected to the common one. Can you see? Connected to here, 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 then connected to here, and then connected to here. Can you see? All connected to the common one, the common plus. Can you see the com here? Here below got one more lah. Okay, I didn't manage to move it here. Okay, here got one more common. Oops. Here. Okay, common plus. Can? Just take note of that. Okay, so this one means what? Means in order to activate this light, to on, like for example this B, right? This B channel, right? This B must be 0 volt lah. Then this thing will on. This LED will on. Okay, can? So this B must be 0 volt. Then it will on. So that's what it means. If this V is 5 volt, then it will off. Clear already? Okay? Okay, so this one is just basically telling you what I just said just now. Okay, here same thing. Okay, so if this one there, it just shows you how to display the digit 0. So this 0 volt, this is 5 volt, right? Common anode. So you see, in order to turn off this G, right? This G is turned off, right? So you must put a 5 volt here. So 5 volt versus 5 volt, there will be no voltage drop. So this part here, this G here won't turn on. Clearly? Okay, there's no current. 5 volt versus 5 volt, got what current? 5 volt across a resistor, right? Then 5 volt. Got voltage drop, meh? Don't have what? This one is still 5 volt, 5 volt. 5 volt minus 0 volt is 5 volt, what? Equals to 5 volt. So this part here, no voltage drop. No, it won't light up, lor. Basically, that's about it. Understand already now? Okay? Quite straightforward, right? Okay, let's move on. Okay, let's move on. Okay, now at this part here, okay, we see common cathode also same thing. But now the difference is this. Okay, for a common cathode display, the common is connected all to the negative one. Can you see? Negative, 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 all negative. Then all the LED face in the opposite direction. Can you see now? Okay. Now in the workshop one, normally we use common anode lah. Because why? We want 0 volt to work ma. Correct not? You want send signal 0 volt. But if you want to do the opposite, that also can. So you must send 5 volt for it to work because it's all connected to 0 volt, the common one. Okay, you send 5 volt into B, it will work. Can? Okay, so it can work this way also. So you decide which one you want to use. We have both in our workshop. Okay, so you just take note of this common cathode. Okay. Okay, same thing like what I said just now. Okay, so to get it to work, you see, you want to put a 0, right? So now everything on. Just now was everything here is 0 volt. Right now everything 5 volt, 5 volt. Then the one that you want to off is 0 volt. Clear already? Okay, that one you want to off is 0 volt. So over here, 0 volt. So 0 volt, 0 volt, then there's no voltage drop. Right now, 0 volt to 0 volt, no voltage drop. Okay, so just take note. Alright, no voltage drop, so it will not light up. Okay, yes, this part here, fill it up yourself. Give you 5 seconds. Go and think about it. I'll pause the video now. You can pause. Okay, now fill up. Okay, now unpause. Does it work? Yeah, it works. Okay, so guys, fill up your thing yourself. Okay. Yeah, these are the answers. Okay, that's all. Right, so guys, I hope that in this segment here, okay, this has helped you understand electronics, this particular topic on semiconductor diodes in greater detail. Now take note of all the important things. These are all the important things only. The rest of the parts of semicon diodes, right, are not important one. You don't need to go and study into detail. Okay, these one are all the exam tested questions. Okay, so make sure you study the parts that I revised here. Right? Okay, that's all. Goodbye.